So now let's and what procedure did we use for solving this MoM? We use this pulse basis and delta testing. Okay. So I am going to show you some results of simulations now to tell you that how you implement the MoM also makes a huge difference in your calculations and therefore what your interpretation you draw. Okay. So let's look at in one case and another case over here. Okay. So typically how will you get more accurate results in your MoM? Increase the number of segments, right. So in other words, you increase this capital N, right, N segments, you increase this N, right. So I want to study, for example, this ZA, which I am going to write as RA plus J XA. So let me look at what happens to RA and XA as I increase the number of segments, right. So I would expect some kind of numerical convergence to happen. So and the antenna length, I am going to choose a very popular antenna length, which is roughly half a wavelength, okay, and it will become clear why I am going to choose half a wavelength, and I am going to choose a very thin radius. So I am going to choose, right. So it's basically a very thin wire, almost half a wavelength, but slightly less. Okay. So yeah, it will become clear why I have chosen this. So supposing I choose the delta testing functions. Okay. So with delta testing functions, what happens is you get something like this. It begins to converge for, by the time this is say 120, you can start with something as crude as, let's say, 20, right. It begins to converge over here, right. So this is your so this is with a delta gap. You may ask, how do I, if I use this procedure over here to find out the input impedance, I will get different answers. I may get different answers depending on whether I choose a delta gap input source or a magnetic frill, because the linear algebra, the matrix and the vector are different. You will get different answers, right. But the answer should not really depend too much on that. There is an input impedance, and that's what I should get. So this is what I get when I look at the right, and this value is roughly about 75 to 80 ohms, let's say. Okay, it's close to 75 to 80 ohms. And what happens to this reactance? So it has a strange, an interesting behavior. So 0, right. It doesn't really show very great signs of converging. Okay, so you wonder what is going on over here. So this is with delta gap. Then you can say, these results are not satisfactory. Maybe the magnetic frill is little bit more accurate as an input. So you can say that take the magnetic frill. Interestingly, what you observe now is something like this for the reactance. So there seems to be a good convergence, but you need to have at least about 100 to 120 segments to get the same value of resistance, right, and you have some confidence that it's about 75 to 80 ohms. And what happens over here is right, the reactance does not seem to converge. So if you saw these results, what would you conclude? As an antenna designer, if you are given these parameters, right, you don't know CEM, you are given the results of CEM. Looking at this, what will you say? These results may not inspire too much confidence, right? You can say, okay, it seems that the real part of, the resistance is around 75 to 80 ohms. This reactance, I don't know, right? It's sometimes, both the methods are giving slightly different results, not slightly, fairly different results. So as an antenna designer, I am in a fix. What I have to make my matching network, I need to know the value of XA, right? So what value of XA do I choose? So this person may come back to you and say your CEM is useless, right? And that would almost be correct, except that, as the point I am trying to make over here is that the choice of MoM makes a huge difference, right. So, this is what we did, the simplest way of doing MoM, pulse basis delta testing. Then you get a little, you know, you've done your CEM course, you feel a little offended here, what is this, my results are not looking good. So, you say, okay, let me do something a little bit more accurate. So, I do pulse basis and pulse testing, right. So, it's like a Galerkin thing. So, what kind of results do I get over here? So, again this is my figure around 80 ohms. This is what you get over here, and mind you this is around 60 and this is around 10. Okay. What do you get with this magnetic frill? Okay. That is all right. The more interesting thing happens over here when I look at the reactive part. So, this was RA and here is XA, N, again 60, 10, okay, and this is about 0. That is what you get with a delta testing function, I mean with a delta excitation, and with a magnetic frill what you get is now when you show these results to an antenna engineer, there is some satisfaction because both methods have converged, right. So, you have a reactive, I mean the resistance part is about, you know, as I mentioned 80 ohms, 75-80 ohms, and the input, the reactance part is almost exactly 0, okay, and both methods are giving the same answer. So, this tells us that the choice of excitation is not so crucial as the way in which you are solving MoM. So, usually when students learn CEM for the first time, they think pulse basis delta testing, if you have done that is good enough, right. But this is telling you that, you know, you have done all the hard work in getting till there, just go all the way and do something a little bit more accurate, you will get this. You will get even faster convergence. For example, in the pulse basis delta testing, you had to go to nearly 120 N in order to get the resistive part to match, to converge. Here within half the number of elements, within 60, you are able to get convergent results, maybe even less than that, right. So, you are saving on computational time, but you have to do a little bit more work to calculate AMN, the matrix elements, right, and you get this answer, right. So, this is something to always keep in mind. Pulse basis delta testing is very good for understanding a problem, it is not good for actual calculations, okay. And yeah, so the choice of this 0.47A is, I mean why would you choose something like that? It is because you are getting a reactive part of nearly 0, right, and the RA comes out to be at 75 to 80 ohms, which is easy enough to match in a regular RF circuit, okay. Is it fine?